let me introduce me. I'm Martin Ziegel from the German Aerospace Center. I'm working at a high-performance computing group for simulation software. I'm actually not an app developer, but I'm doing lots of simulation codes actually. But today I want to talk about how to bring these apps and software, simulation software, into environments. So a short outline of my talk, some introduction. I want to talk about actually why you want to have native code with Android. And I want to talk about our app that we ported to Android, which is used at the German Aerospace Center for aircraft design. And I'm going to talk a bit about hacking, so all these steps that you have to go through when you want to develop native app development. So you want preparation steps, all the steps in compiling third-party libraries and patch your code, and how to use the Java native interface to communicate between Java world and the C++ world. And I'm also doing some coding. I hope you won't be bored with this coding stuff. Finally, I'm going to talk about then how to integrate this native code building into the Gradle build system, which is a new build system used in Android. And I'm going to talk about some slides how to run that on an Android emulator efficiently, since these apps tend to be quite CPU intensive. So, yeah, why do we want to have native code in Android? Probably because you already have a large software, a large code base already tested, and it's just not reasonable to rewrite that to Java, because you're probably introducing new errors. Your code also might depend on a third-party library, which just don't exist in Java, and it's also too time-consuming to do that. And in addition, there are lots of numerical algorithms which are implemented in C and Fortran, and you want to use that. And third, maybe you don't want to hear it as Java people, but the Fortran and C compiles are much faster and use much better optimized code. On the other hand, of course, native code is much harder to debug if you have problems. It's not that easy as when you just get a stack of trace in Java, and you have to port your app, and you also have to rewrite platform-specific code, of course. So, some words about the app we ported for app graph design. It's called Tegel Geometry Library. It consists of a central geometry viewer and library, and it's used by many simulation tools at the German Aerospace Center for designing aircraft and spacecraft. It's written in C++. It has a quite large code base, and the most important is tested. And we're using other third-party libraries, and the most important one is the Open Cascade CAD kernel. So we're using a CAD kernel inside our tool to create the geometries, and this one consists of 4 million lines of code, so you don't want to rewrite that, right? And for the visualization, we're using the OpenSea graph rendering engine, which is based on OpenGL, and also you don't want to rewrite that. It's a multi-platform tool, so it exists on Windows, Linux, Mac OS, and now also on Android. And it's open source, and you can check it out for yourself. This is how it is used actually in the DLR. In the middle you see the Tegel viewer. It's just visualized geometry. Tegel is much more than the viewer, but so you can see what it's about, and you can use it, for example, to feed aerodynamic computation tools. So you're creating your surface mesh, and then you give it through the aerodynamic simulations, or you export your geometry into CAD systems, or you can also visualize the geometry with Blender, for example, or even print that You can export STL files and print the aircraft and just have a look at what they look like. This is what the view looks like on the different platforms, and on the bottom there is the Android one. It just looks different because it's other, it's different, but the backend, the complete computation, the rendering is the same. So you might ask, why do we want to have an Android port DLR? Are they insane? Are they just stuff on the Android hardware? No, actually there was no real reason. The only reason is because it's fun and we can do it, right? We just did it as a fun project actually, but we just want to share how we did that. So now let's come to the major topic here in this talk too, about hacking. So about the steps we are going through for the report. So here's a short checklist. What you actually need in order to do this development. So you need, of course, Android SDK, and then in addition, you also need the Android native development kit called SDK, and it consists of cross-compilers, GCC. It has a build tool called NDK build. It's just based on makefiles actually, and it has a debugger based on TDB, and of course also Android-specific libraries to talk to the Android backend, for example, to do some logging or whatever, to read sensors. And when you want to port third-party libraries, you also need CMake or tools, whatever this third-party libraries need. So now I'm going to talk about the steps you're going through when porting your code. So first install the SDK NDK, that's obvious. And then, this is quite hard part actually, you have to cross-compile all these libraries and your code you need. And if you're not lucky, then you also have to fetch those things. Then if you have that, you have to define a Java interface class to talk from Java with the native code, the C++ code. Then you have to write by hand a glue code in C++ which connects the Java interface and the C++ code. So that's the JNAG glue code. Then you're creating or compiling a shared library which you can use with your calling from Java. And what we did is we designed a Java-based Android user interface. So we have a hybrid application, a user interface in Java and a backend in C++. And the Java part talks to the backend. And finally, we build the app, compile native code using standard build steps. And today I'm going to talk about these high-level steps here. So this is just an example when we ported the OpenScape library, the CAD kernel, to Android. And as I already mentioned, it's quite huge. So there were some platform-specific code path in there. For example, there is a difference in the Android C library compared to the GNU C library. It's the Bionic C, which is part of Android. For example, there's no time zone function. We had to work around that. Also, the password structure, it's a standard structure in the C library, is a bit different. The PWG member is just missing, which consists of, which has some user information saved. And more important, the Android kernel don't have the IPC calls, so you don't have calls for shared memory operations and for the specific methods for releasing and setting semaphores. So we had to find workarounds for that. But what you can do, that you're using this if-def statement, you can ask whether you're compiling for Android or for desktop. And on Android you have this statement _Android _ defined. distance, so you can just get from the code on which platform you're compiling. And then we had to deactivate all the X11 server-based code path on the rendering part of the OpenCascade kernel. So what we did actually is just disable the rendering engine completely from OpenCascade, since it uses X11 and the fixed function OpenGL pipeline, which we didn't want to use, and replace that with OpenSymra. So the next step, we had to compile that after patching, and it's a CMake-based toolchain. And what you have to do is, or what you can do, is that you install on your computer a standalone cross-compiler toolchain with the NDK. The NDK has a script, make standalone toolchain, where you just define your target platform, the target directory, you want to install that, and then you get a complete standalone toolchain and use that for cross-compilation. And then you're creating a CMake file where you just define where your standalone toolchain is located, what your compilers are, and important are these last 3 lines of code in order that you prevent the compiler using your native libraries and so your desktop libraries and your desktop interface. It should only use these includes and libraries from the native toolchain. And then you're going on, you CMake with this toolchain file, and then all these little steps are like with standard CMake projects. In the end, you have a shared library with native code for Android or for ARM or whatever. Now I wanted to talk about like how to speak between these both worlds, the Java world and the native world. And we are using the Java native interface for that, which enables us to communicate between these worlds. And it's realized by just calling functions from shared libraries, and on Android, these libraries are the .so files. And JNI provides mechanisms to load these shared libraries with some system calls, and also it has some functions to convert data types between Java and C. But what's not so nice is that you have to write the glue code for yourself. You cannot do it automatically, at least not that easy. What's also important is when you define your native interface, you really have to be careful how you call, you name your C functions, glue code method names. And in order to do that right, you're using the tool JavaH, which does it automatically. That's kind of nice. And I'm going to show it now how to do that. So first, in the first step, you're defining your interface class, and now I'm switching to my Eclipse. I just want to present here a really small, simple app, how to build up such communication between Java and the native. So we have here a really simplistic app, just 3 buttons. It actually does nothing at the moment. And now I have here the JNI folder where I put in my native code. And I created here a small library just containing of 3 functions, a Fibonacci code. It's recursive defined, so quite compute heavy, not really clever made, but just for demonstration. And 2 functions for setting and getting a string out of the library. So this is the C part, and what you have to do now is you define an interface for that. And that consists of two steps here. In the first step, you're loading your compiled library in the first step, and in the second step, you define your methods you want to talk with. And the important thing is that you call them native, so that Java knows it has to load these methods from the shared library you how to do that together. So I'm gonna run now the Java H command, as I already said. I'm going into the JNI folder and call the Java H on my Droid Core native class I already made here. I'm already done. So what we now see is, if I refresh, I got a new class or a new header file here, and it's completely created automatically by Java H. And this is the blueprint what we're going to have to implement. And I'm now creating a CPP file with the same name. Let's do this. File new CPP, and we're including this header file. And we are also including the header file of my library, which I want to use. And now we're going to use some Eclipse magic to make the implementation for ourselves. So implement method, we're selecting everything and press finish. And now we have the bodies of our functions, we just have to implement them. So then also we have to add this code here to the make file. Don't have to forget that in order to be compiled. So and now we want to call, let's go to the first function. We want to call the native Fibonacci computation. So what we just have to do here is we call our library code Fibonacci with the argument n, which we define here. That's everything. Now it's getting a bit more complicated. Here the getName function should get a string from C, convert it to Java, and return that to Java as a Java string. So what we have to do is, we have to ask the Java native environment to convert us a C string, and we're doing it by using the JNI env object, new string UTF will do that for us. And now we're just calling again our library, mylib / getName, and we're asking for the C string, returning that everything is fine. And try to compile that. Okay, no errors here, that's good. So let's come to the last method here. Here we're doing vice versa. So we get a string from Java, have to convert it to C string and give that to our library. So first we need a, let's call that here the name. And we also need the environment again. So we have our C string. And we are calling, we're using the function get string UTF characters, which transforms the Java string name into the C string CSTR. With this string we can call our library, set name C string, and now we're not ready since we have to release this C string again. C is a bit messy, we have to do the memory management by ourselves, so we have to do that here. We have to deallocate the C string, and we are not allowed to use delete, but we have to use a function from the JNI environment, which is called C string release UTF characters. And as an argument, we give the Java string and the C string, and that should be it. So what I did now is I just coupled the Java code and the C code. And now I just have to call this code from the Java inside. So for now I'm just calling on the emulator, running this code which we already have. So now, for now, it just don't do anything. So it just say, okay, I pressed on one of these buttons, nothing fancy, and we want to connect that. We're going into our activity and just call the C functions as normal Java functions. So what we are doing here is we store the result of Fibonacci droid.conf native dot Fibonacci number n and save that into the text view at the top. Set text integer value of result to string. So now we can display the computation of the Fibonacci code in the view, and we're doing the same here also for the set and get name functions. So droid native get name will give us a string. We are just displaying that on this text view. Name. And finally, with the set name, we are just taking the text out of the text box and giving it to the native code. So droid native set name text dot toString. So now our app is ready to be called, to be run. Let's have a look. So what you're seeing is now I can enter here some numbers and the Fibonacci code should be called. You can figure that, okay, the 10th Fibonacci number is 89. Let's go up a bit, 35. And there we are. So it's quite fast. Okay, if you go up with this number here, if you go up to 50, then it will compute quite long. Since it's a recursive operation, we have this tree, but just for demonstration. So that works. Just call get name, and this is the library just returns default name now. And I can change that by entering hi droid.conf community. Now I'm setting the name, and if I'm pressing get name, we should have that there. So that's the demonstration. Now I'm coming to a part which is quite important. It's about the life cycle of native code, and it's different compared to what you have with the Java code. So we're skipping this. I already did that here in the tutorial. So you probably know that an Android app has several steps in life cycle. So you have different states: started, resume, pause, stop, created, whatever. These steps don't exist in the native code. There is just one, or there are just two steps actually, not loaded and loaded. So before your library gets loaded and after, and your native library resides in memory even if you close your app. So it remains the state, and that's quite important. You have to be careful when dealing with that. In order to show you what I mean, just go to the emulator back. So I'm just closing the app here. You can see at the bottom there's still the HiDroid.conf community and the 35 inserted in here. And if I go in, like, everything is set, reset. But now, if I press get name, suddenly HiDroid.conf community is still there. And that also works if I'm suspending my device and go back again, suspending. Let's have a look what's happening if we get the name. It's still HiDroid.conf community. The only way to reset for now the app is to completely kill it. And if I now press get name, I get the default name. So if you don't want this behavior, you have to write it by yourself. You have to call some cleanup functions from your Java code to the native code. So some words about compiling and packaging when you have native code. And it's just about how to integrate the NDK build into the Gradle build system, which is the new build system for Android, which it replaces Apache End, and it's already used by Android Studio. But the NDK integration into Gradle is just integrated recently by Google, and it tries to create the makefiles by its own, which mostly didn't work or don't work. So as a workaround, you can disable the automatic creation of Android makefiles. You write your own makefiles, as I showed before, shortly, and you have to define a custom build task in order that you run the NDK build command, else you won't get your library and you probably get some crash. And this is how you do that. So you have to register the libs folder inside your app source folder. That this libs folder gets included into the APK file, and you're defining the JNI source use variable and setting it just to 0. With that, you prevent automatic makefile creation. Then you define a custom build task. So you just say, okay, please call NDK build command, and you just decide whether you're using Windows or not. You have to use different NDK build commands. And what you can also do is you're providing the -J argument for NDK build, which allows you to do parallel builds, so you make up the build much faster. And runtime available processors gives you the number of processors in your computer, and if you have all, then you're compiling for CPP files at one time. And finally, you just have to add this newly created task to the compiled task, or that Gradle knows, okay, I have to call that before packaging everything. So my almost last slide here is about using emulator efficiently. I have already showed you with that simple example an emulator. The problem is that the standard Android virtual device is pretty slow, since it emulates ARM instructions using the QEMU software, and if you have CPU-hungry apps, then it gets really, really slow and painful. What you can do, and what we heard about before, is you can switch to an x86-based emulator with GPU acceleration. And you only have to do is use or install the Intel AXM acceleration driver, which is part of the Android SDK. Then, of course, you have to recompile third-party libraries with an x86-based toolchain. You cannot use your compiled ARM code, of course. And you have to add the x86 to your application MK, which is in the JNI folder. So in addition to the ARM eAPI, you also add x86, and you get for both worlds your compiled code. And this is then how it looks like. Now I'm trying to run the actual application we recorded here, which is that one. And you see this is the graphical view, and now I'm gonna load some Airplane, which is computed on time here. You really see the kernel is working now, and there we are. So it's pretty fast and performant. You can here select everything, you have animations, whatever you want. So this is a really good way to use the emulator. Okay, and as you probably have seen, that was not a standard emulator. It was the Genymotion Android emulator, which is also x86 based. And for me at least, it works much better than the standard emulator. It uses VirtualBox under the hood and comes with many pre-configured devices. And for me, it just works. And this is how it looks like. The app is in store since Monday, I think. For free, of course. It's a really small app. But yeah, you might check that out and give us some feedback, what you think about that. We will be glad. So So, yeah, do you have any questions? Just for important remark, you can write me email, and the sample code, what we did here, what I did here now, is also on GitHub if you want to check that out.